Welcome back, everyone. Today we're doing another deep dive into some really cutting-edge AI research.
That's right.
Have you ever stopped to think about what's actually going on inside a large language model when it seems like it's, thinking?
It's more than just the words it spits out, right? There's this whole complex computational process happening underneath.
Exactly. A whole universe of computation. And today we're diving right into that hidden world.
It's a pretty exciting area. We see these amazing outputs, but the actual multi-step inference, the reasoning happening inside the model's internal states, that's often invisible.
Kind of like peeking behind the curtain.
Yeah, precisely. To see how the magic really works.
Well, our mission today is to unpack the paper MAP, a survey on latent reasoning by Ruigi Zhu and the team. It's a really comprehensive look at how LLMs are starting to reason without explicit language.
Purely within their internal states.
Right. And if you're working in AI or ML, you'll want to pay attention. Understanding this is pretty critical for figuring out where models are heading next.
Absolutely.
Okay, so let's kick things off maybe with a quick 1-minute rundown of the paper's core ideas. Good for a quick takeaway.
Sounds good.
All right. First up, we all know chain of thought, LLMs, verbalizing reasoning steps. It's been huge for accuracy, for interpretability.
Definitely a game changer.
But, and here's the catch, it's bottlenecked by natural language. Each token, each word it generates carries surprisingly little information, only about, 15 bits?
Yeah, it's quite limited when you think about it. So to get around this, the paper introduces what they call Latent COT.
Latent COT.
It's a big shift. The idea is that multi-step reasoning happens entirely inside the model's continuous internal space, its hidden states. No explicit words needed.
And the difference in information bandwidth is just wild. 15 bits for a token versus
the full hidden state. We're talking maybe 2,560 dimensions, FP16.
Yeah.
That's around 40,960 bits per step.
Wow. That's over 2,700 times more information per thought step.
Exactly. It just unlocks this massive potential for richer, non-linguistic reasoning pathways.
Okay, so that's latent COT. What else does the survey cover?
Well, it breaks down the methods really nicely into two main categories. Vertical recurrence, think deeper computation within layers.
Okay.
And horizontal recurrence,
Yeah.
which is about expanding the model's capacity across time, handling longer sequences.
Vertical and horizontal. Got it.
And it even looks ahead towards infinite depth reasoning, especially using diffusion models, really pushing the frontiers of LLM cognition.
So understanding this internal latent stuff isn't just academic. It's key to building, stronger, faster, maybe even smarter AI.
It's fundamental, yeah. Moving towards truly scalable models.
Okay, great summary. So to really get it, maybe we should lay down the basics of this latent chain of thought, LCOT framework first.
Good idea. So picture a transformer model processing information. You've got the input at any point, let's call it activation X.
Right.
And then you've got the hidden state, S. That's basically its internal memory. Everything's understood up to that point.
And these hidden states, they aren't all the same, are they? The paper mentions different types.
Exactly. There's the standard KV cache, key value cache.
Yeah.
That's like the transformer's short-term scratch pad, storing bits of processed info. It grows with the sequence.
The typical one.
Yep. Then there's something called a linear attention state. That's more like a fixed size summary, constantly updated. It's more efficient for recurrent processing.
Okay, big size.
And finally, especially in approaches that look more like old school RNNs, the hidden state might just be a single vector condensing everything learned so far.
Compact.
Right. And this flexibility helps us see how the actual operations break down into two main types: spatial and temporal transformations.
Okay, let's unpack those. Spatial first. What's that?
Spatial transformations, think vertical reasoning. This is classic transformer stuff. Information moves deeper through the layers, but at one specific moment in time.
Like signals going up through the floors of a building.
Exactly. Each layer builds on the last. Deeper processing.
Gotcha. And temporal.
Temporal transformations or horizontal reasoning are different. Here, the model iteratively refines its understanding within a single time step. It takes its current internal thought, its activation, and applies the same transformation function again and again.
Like rereading a sentence to understand it better. A loop in time.
Sort of, yeah. A computational loop focused on refining that one moment's thought.
So the big difference. Explicit COCO takes these internal thoughts, these continuous representations, and forces them into discrete words we can read. But latent methods, they just skip that whole decoding step. They keep the reasoning flowing in that rich, continuous internal space.
And the huge advantage there is exploring pathways that aren't limited by language. Maybe finding more efficient, more clever solutions.
Solutions we couldn't even express easily in words.
Potentially, yeah. The downside, naturally, is interpretability. It's harder for us to follow the steps when it's all happening in this hidden, continuous space.
Right, makes sense. Less transparent.
And what's also interesting is how diffusion models fit in. We usually think of them for images, right?
Yeah, generating images.
But they inherently work through iterative temporal updates. They refine their output over many steps. It's a different dynamic from the usual spatial temporal mix in transformers.
But they're getting mixed now, like this DKV cache thing.
Exactly. Models like DKV cache are bridging that gap. They integrate transformer-style memory, the KV cache, into the diffusion process. So they bring some spatial layer-like updates into each denoising step.
Making the refinement more targeted.
Yeah, more efficient. It means these diffusion models can look at a whole sequence, figure out the high-confidence parts, and then refine everything in parallel, step by step.
Which is totally different from standard autoregressive models.
Totally. Autoregressive models make a decision, one token, and move on. They can't easily go back and fix things earlier in the sequence. Diffusion models can revisit and refine globally.
Okay, that distinction is really helpful. Which brings us neatly to the paper's main categories: vertical versus horizontal recurrence.
Right. The core distinction, like we touched on. Vertical is about getting more computational depth by looping within the layers, making the model think deeper on the spot.
Deeper thinking.
And horizontal is about expanding the model's memory or attention span over time, letting it handle much, much longer sequences or contexts.
Longer memory. Okay, let's tackle vertical first, these activation-based methods.
So the goal here is deep, recurrent computation without generating explicit tokens. A key early idea was the universal transformer.
Ah, yeah, I remember that.
It introduced adaptive computation time, ACT, basically letting the model decide how many internal steps, how much thinking to do for each input. Dynamic depth.
And things have moved on since then.
Oh yeah. We're seeing this trend towards a more modular structure, sometimes called pre-loop coda.
Pre-loop coda, like music.
Kinda. An initial phase to process the input,
Right.
Then a dedicated iterative reasoning phase where the looping happens, loop, and a final phase to shape the output, coda, more structured computation.
Makes sense. And other trends.
Well, designs are getting smarter about handling input during iterations, managing memory more efficiently, sometimes reusing memory slots. And interestingly, explicit depth embeddings seem less critical now.
The model just figures out where it is in the loop.
It seems like it, yeah. Simplifies the architecture.
Okay, what about this activation with explicit hidden state feedback? Sounds different.
It is slightly different. Models like Coconut or COT-Former, they take their internal state, their thought vector basically, and feed it back into the input sequence.
As if it's a new word.
Exactly. But it's not a word, it's the raw hidden state. A clever trick to deepen computation internally without the latency of generating text. Keeps it all latent.
Very neat. And then there's training-induced recurrence, so no changes to the model itself.
Right. You take a standard transformer, but you train it in a special way so it learns to perform recurrent computations implicitly. The training forces it to develop these internal loops.
How does that work, like continuous activation recurrence?
Yeah, that's one way. Like Coconut, where the last hidden state just gets looped back as input for the next internal step. Or Cody, using self-distillation to make recurrent states align, essentially teaching it iterative refinement.
And System 1.5 reasoning.
That one dynamically allocates thinking depth, making inference way faster while keeping Cody accuracy, all inside of standard transformer architecture. It's pretty impressive.
Wow. Okay, and compressed state recurrence. Condensing thoughts.
Yeah, the idea is to compress the intermediate reasoning steps into smaller representations, sometimes even discrete gist tokens. It effectively turns horizontal, step-by-step thinking into a vertical, deeper computation for each logical step.
More bang for your buck, computationally.
Kinda, yeah. And you won't believe this next one. Iteration expansion through strategic tokens.
Strategic tokens, like placeholders.
Basically. Even things like filler tokens or learnable pause tokens can give the model extra implicit steps for internal computation, and more structured planning tokens can trigger whole internal subroutines or loops.
Just by adding a specific token, that's wild.
It shows how flexible these models can be. Of course, training these recurrent setups needs care.
Right, stability must be an issue.
Definitely. So you see strategies like progressive stacking, gradually adding recurrent depth during training, or stepwise internalization like in Coconut. And methods like Relay try to explicitly align the internal loops with the actual reasoning steps needed for the task.
Makes sense. You need to guide the learning. So what's the payoff? What can these recurrent models actually do better?
Some really cool stuff is emerging. Algorithmic generalization, for instance. Models trained on small problems can sometimes solve much harder versions just by being allowed more internal thinking time during testing. More loops.
Like how humans tackle harder problems by thinking longer.
Exactly.
Yeah.
Mimics that progressive problem solving. And in symbolic reasoning, they can simulate algorithms, like graph searches within fixed memory. They're better at multi-hop reasoning too, building these internal computation structures.
And even implementing optimization.
Yeah, some models seem to implicitly learn gradient descent steps internally. It shows this deep link between their reasoning process and how networks actually learn.
Fascinating. Okay, let's switch tracks. Horizontal recurrence. Hidden state-based methods.
Right, so vertical depth has limits. You can only stack so many layers physically. But temporal depth, processing sequences, that could go on for millions of tokens, theoretically.
But the memory explodes, right? That's the classic transformer problem with long sequences. The KV cache just grows and grows.
Precisely. So the solution here is compression. Compressing the history into a fixed size representation, like a vector or a matrix. Much more like traditional RNNs or state space models.
Oh yeah, how do they do that?
Two main flavors here.
Yeah.
First, linear state recurrence. Think Mamba 2, GLA, RWKV6. They use a special matrix as their hidden state. It continuously summarizes the past, getting updated at each step.
Like an efficient, always up-to-date summary of the past.
Exactly, a compact memory.
And the second flavor, you said this gets really interesting.
Yeah, gradient state recurrence. This is where the thinking gets really meta. The paper highlights this view where the update rule for the hidden state matrix is mathematically like taking a gradient descent step.
Wait, like the model is optimizing something as it processes the sequence.
That's the insight. It reframes this temporal evolution, this step-by-step processing, as a kind of continuous iterative optimization. It conceptually links horizontal recurrence over time with the deep layered reasoning we see vertically.
That's a deep connection.
It is, and models like TTT, Titans, ATLAs run with this. They treat that hidden memory matrix as if it were fast-adapting parameters, and they update it using a learnable optimizer.
So optimization algorithms like SGD or ATOM are literally built into the state update mechanism.
Yes, learned optimizers shaping the model's internal state evolution.
Okay, mine's slightly blown, but how do they parallelize that? Isn't recurrence inherently sequential?
That's the challenge.
Yeah.
But the solution is clever. Chunk-wise parallelization. Instead of one word at a time, process the sequence in small chunks or paragraphs.
Process chunks in parallel.
Right. Process each chunk quickly, maybe recurrently within the chunk, and then combine the resulting states.
Yeah.
It's a balance between the expressive power of recurrence and the need for speed.
A practical compromise. Makes sense. And like before, can you induce this hidden state stuff through training?
You can. Training-induced hidden state conversion. Taking a pre-trained transformer and fine-tuning or distilling it into a more efficient hidden state model, like an RNN or an SSM.
While keeping most of its knowledge.
That's the goal, yeah. Preserve performance, but get constant memory inference, huge for deploying large models.
Any examples?
Sure, SuPRA converts models like Llama 2 by swapping attention for linear components and fine-tuning. Mohawk turns transformers into Mamba-style models. Llama scales this up, showing these converted models can match powerful teachers like Llama 3 with way less compute.
So conversion is a viable path.
Looks like it. There are also methods using low-rank approximations, gated mechanisms, lots of activity trying to get the best of both worlds, transformer pre-training power, and recurrent efficiency.
Okay, this is fascinating stuff. Let's shift focus a bit to interpretability, mechanistic interpretability.
Right, the big question here, are the layers in a transformer actually doing distinct computational steps? Are they the units of reasoning?
And the evidence suggests.
Increasingly, yes. There seems to be this layer-based hidden chain of thought. The way layers are stacked seems directly linked to reasoning power.
How so, at a high level?
Well, studies show correlations. More layers often mean better reasoning on certain tasks. Some implicit reasoning capabilities seem strictly gated by layer count. Two-hop reasoning needs, say, 2-3 layers minimum. It's even been formally shown layer depth is a key bottleneck for how many internal reasoning steps a model can take.
So more layers, potentially more reasoning steps.
At a macro level, yes. And at a micro level, we see functional specialization. Different layers seem to do different jobs, kind of like steps in an explicit OT.
Which leads to this theory of layer specialization.
Exactly. The idea that layers aren't just generic processors, they systematically specialize. Shallow layers near the input. They handle the basics.
Like syntax, local info, basic facts.
Yeah, basic representational processors, connecting entities, understanding structure.
And the middle layers.
They seem to be the core of Latent COT. This is where specialized circuits for complex functions emerge. Their internal representations, their embeddings, can actually be better for some tasks than the final output layers.
Really? Better than the final layer?
Up to 16% better on some text embedding tasks, according to the paper. And they have a real causal impact on reasoning, like how specific middle layers in GPT-2 were found to be crucial for identifying indirect objects.
Okay, so middle layers are key reasoning hubs. What are the deep layers near the output?
Their main job seems to be integrating everything and refining it for the final output, decision-making.
But there's a downside, the curse of depth.
Sometimes, yeah. Very deep layers can sometimes train poorly, might not add much unique function, or even degrade performance due to issues like variance or attention patterns breaking down.
Interesting trade-offs and information flow between layers.
Crucial. The theory of information flow highlights how attention isn't just about the input sequence. It allows information to move between layers. Things like back attention. Let higher, more abstract layers feed insights back down to lower layers.
Connecting the dots across the whole network depth.
Precisely. Essential for complex reasoning.
Okay, this layer-centric view is compelling. It even ties into Turing Completeness.
It does. The paper touches on whether transformers can, in theory, compute anything a universal computer can. RNNs were proven Turing complete ages ago because they're naturally recursive.
And transformers?
Well, proofs exist showing they can be Turing complete, first with some ideal assumptions, but more recently even under practical constraints like constant precision arithmetic. So, theoretically, they have universal computational power.
But the really wild idea is that prompting with chain of thought might make them Turing complete in practice.
Yeah, that's a fascinating perspective from Q and colleagues. The idea is that the COT process turns the transformer into a kind of dynamic computational tape. Even a fixed depth transformer might simulate complex circuits if you give it enough COT steps.
So computation isn't just in the weights, it's also in the interaction.
Exactly. It's a powerful idea. It gives us this unified view, thought unfolding in two dimensions, horizontally along the sequence via explicit COT.
And vertically, through the layers via implicit latent COT.
Right. Both are ways the model expands its computational power to solve the problem.
Wow. Okay, so where does this all lead? The paper talks about towards infinite depth reasoning. What's the goal there?
The ultimate goal. Models that can spend potentially unlimited thinking time refining a solution, not bound by a fixed number of layers or steps.
How do we get there? Diffusion models seem key again.
They offer one route, spatial infinite reasoning. Because they work on the whole output sequence iteratively, they can refine globally, start with a rough draft, maybe noisy or masked, and improve it step by step.
Unlike autoregressive models locked into their past decisions.
Exactly. Diffusion allows global planning, consistency checks, self-correction, and you can often choose how many refinement steps to run, even at inference time. More steps, potentially better answer.
And there are different types: masked, embedding-based, hybrid.
Yep, masked models like D3PM work on text with masks. Embedding models like Diffusion LM work on continuous representations. And hybrids like Llama try to combine the best of autoregressive for coherence and diffusion for refinement.
Interesting architectural diversity there. What's the other perspective on infinite depth?
The optimization-based perspective. This really ties back to that gradient state recurrence idea.
Grading time for depth.
Exactly. If updating the hidden state is like taking an optimization step, then processing more tokens over time is like running more optimization iterations. You get deeper reasoning without adding layers.
Through strategies like infini-attention.
Right. Infini-attention uses a special compressive memory per block, allowing theoretically infinite input sequence length with constant memory. A linear delta rule for updates.
And test time training, TTT.
TTT and its successors, like Titans and Atlas, literally run optimization algorithms, like SGD or Atom, on the hidden states during inference.
Optimizing the thought process on the fly.
Pretty much. It really hammers home the idea. You can get deeper by thinking longer in time.
And implicit fixed point RNNs.
Those iterate internal blocks until the state stops changing much until it converges. So the depth is adaptive. It stops when further refinement isn't helping.
So the unifying idea is depth emerging from optimization over time.
Yeah, the hidden state acts like a fast adapting layer, constantly refining itself.
Okay, what an incredible tour of latent reasoning. So wrapping up this deep dive into the MAP survey, the big picture seems clear.
Yeah, latent chain of thought is a fundamental shift, isn't it?
Definitely. Moving reasoning into this internal continuous space, it feels like a major step towards, well, more expressive, maybe more efficient, certainly more powerful AI, freeing models from just mimicking human language steps.
Though, as the authors point out, actually comparing all these different methods empirically is tough right now.
Because of different training setups, benchmarks.
Exactly.
Yeah.
We really need a unified way to evaluate them to see what truly works best and when.
Yeah.
That's a big next step for the field.
Makes sense. Well, this leaves us with a pretty mind-bending thought for you, the listener.
Go for it.
If these LLMs really can think in an internal continuous language that's potentially far richer, far more complex than our own human language, what new kinds of intelligence, what new problem-solving approaches might emerge? Things we can barely conceive of because we're bound by words.
It's a profound question, really gets you thinking about the future possibilities. And if you want to dig deeper into the specifics we discussed today, definitely check out the paper's GitHub repository. It's called Latent COT Horizon. Lots of resources there to explore this super fast-moving field.
Excellent suggestion. Latent COT Horizon. We'll put a link somewhere accessible. Until next time, keep exploring the deep end.